we'll start kicking things off with our next speaker, Alexei Linde from Stanford, who's known for his contributions to inflation. So take it away.
Okay, so let me try to speak about what I'm doing, but first, just a few words about Steve Weinberg, because we kind of met with him professionally several times, and the first was my first paper on anything related to physics was about phase transitions in Weinberg's model, and then it continues. I remember how in '84 I visited Gorky, where Sakharov was in exile, and we discussed physics, different problems, and I told him about multiverse, and then we discussed cosmological constant, and then after that I returned home, and then each of us, Sakharov and I, independently have written 2 papers on entropic principle and cosmological constant problem, and of course nobody cared. And then in '87, 3 years later, I found this paper by Weinberg, and I thought, this is the 3rd one. Okay, in Russia, when people are drinking, then somebody bring a bottle of vodka, and they need 3 to drink. Well, the 3rd one did not help for a long time. Nobody paid attention, but you know, it was a great work clarifying everything that what he did. Well, oh, I am not loud enough. Thank you so much. Do you hear me? Okay, then it's okay if you miss the previous words. The next will be better. Okay, so what happened is that sometimes Steve would call and invite me come here. And I remember just once I came, and he discussed some physics with me, everything was fine. And then he said, you know what, I would like to invite you to a club here. And I said, yeah, club, okay, yeah, that's fine. But I was from California, so I came with my sandals and with shorts and t-shirt, and that was it, okay? And he looked at me and said, nope, it does not work. I said, what can I do? Just don't go? No, we'll go. So he gave me his suit, his pants, his shirt, his tie, and his shoes. So for the whole day, I was in Steven Weinberg shoes. And what was amazing about it is that I'm not really a suit-able man. I don't wear them. But this is the first time when I really love it. I looked at the mirror. I have seen absolutely different person. It was so light brown. It was so soft and still keep the form, but just a little bit bigger than for me. But nevertheless, it was so totally great. And I would not tell you this story, but this is what I've seen here. I've seen Steve wearing my suit. Oh, well, anyway, so let me go to my shop. I am in all of this inflation business, which is something which was so bad for this country. But one of the successful first simplest possibly version of inflationary theory is just a theory with quadratic potential. Nothing can be simpler than that. I called it chaotic inflation because you just put scale field here or here or here or here, and then let it roll. And typically it leads to inflation if you start sufficiently high. And then in fact, if you start too high, then eternal inflation starts. So this model has many, many regimes. And it would be perfect, except for many, many years ago, it was shown that gradually, step by step, it was outside of the range which is allowed by experimental data. I don't know what this projector does it because there are so many sophisticated colors here, but I guess this is a Windows interpretation of Apple, okay? Because it's files produced on Macintosh. Yeah, so here, this is the place which is right now compatible with experimental data. And it was necessary to change the models. And one of the way to change the models was this. These are alpha attractors. Sorry for those who have ever seen my talks about this, because for 10 years we still continue developing it. But let me explain the general idea. And yes, I promise that there will be many equations, but there will be a movie in the end for those who will survive. Okay. So this is normal m squared phi squared theory. This is a kinetic term, there's gravity. That's all the theory. This is the same term. Here I changed a little bit kinetic term. A little bit made it singular. But the singularity does not hurt because you can just solve differential equations saying that this is equal to d phi, whatever, different variable. And once you do it, this potential becomes tangent. Actually, this is a typo here in my talk. Tangent squared, okay? And if you take any function v of phi, it becomes v of tangent. It was in the previous version of my talk, but it was screwed by Windows so much that instead of all of the symbols, there was garble, so I just deleted the slide. My talk became just a little bit shorter. Okay, but the point is that if you do this trick, then magic things happen because v of a tangent, and the tangent at infinity is a constant, then it becomes some kind of constant. And the experiment, the prediction for experiment depend only on two quantities, the height of this plateau and the new parameter alpha. That's it. You can change, you can add phi squared plus phi to the fourth plus phi to the sixth with whatever coefficient. You calculate radiative corrections, some logarithms appear, does not matter, it will give you the same prediction. So that's interesting property of this class of models, which made us, well, very interested in them. And there are two different classes of such potentials. One is the tangent squared, and another one minus exponent squared. And for those who follow, if you take this alpha equal 1, it will be Starobinsky model. But this is just a general class, and this general class follows from different principles. And these different principles difficult to explain in such a short talk. But what is important is that these kind of kinetic terms, they are very important, sometimes met in supergravity models inspired by string theory. So this is something more than just fitting experimental data by a certain class of the potentials. And there is also another property of these theories. There's some preferable range of these alphas such that the 3 alpha, it is 1 to whatever 7, and that's it. This is more related to the models influenced or suggested by Kaluza-Klein's theory or string theory. And this is what in plans of CMBS4 or Lightbird to find. So this gray area are predictions of this theory for different values of alpha continuous. But if you concentrate on those which are influenced by these 3 alphas, then these are these purple lines, okay? And one of these purple lines is close to Starobinsky model and Higgs inflation, but it is more general. So this is what we are doing until now. And again, oh my God, again, all is green. That was really blue and violet, whatever. What was here? This is a prediction of Starobinsky model. This, and simultaneously Higgs inflation. they're slightly, one should not use really the point for that, because depending on the theory of reheating, this point slightly moves to the right, to the left, just like these lines and this everything in between. So everything in between is covered by alpha attractors, and they end up at the Starobinsky model and actually go down. Down, I mean, Starobinsky corresponds to alpha equal 0, you can equal 1, and we can go below, which means any small value of ratio of tensor perturbations to scalars. And if, to show the universality, you start with the model phi cubed, phi squared, phi whatever degree, at small alpha, they all zoom, and now these colors look right. So this is just free choice of the, Microsoft Office. So here everything is correct. Okay, so all of the predictions at small alpha meet the same point. So which is what made alpha attractors attractive to us. Not only nice, but they just zoom to the same place. Okay, and this again, this is from Lightbird papers. They're planning experiments for the future, well, flying in 23. Maybe it will change. Okay. And that is about their targets. So these are purple lines, and this is gray line, and whatever they find, if they find it there, that would be fantastic. And now I'm going to tell you about something totally new, and that is a result of our work during last 2-3 months together with Renata Kalish, and 2 more collaborators joined us right now. This I will show you in the end of the talk, explaining the meaning. That is, okay, we'll see now. So what is that? Some formal part of it. I will not drag you through all of these considerations and equations. The fact is that there is some system of theories which have SL2Z symmetry, which are closely related in their structure to alpha attractors, but more complicated. And they have this symmetry, which, according to some people, are stable with respect to string theory quantum corrections. So they are interesting for their internal reasons. But for a while, and until pretty recently, there was no interesting potentials which would give you this Plato potential, which would help to get inflation. And this part recently changed. So without, well, this is just an example of one of these potentials. This is a strange thing here, g of I, g of tau, whatever. This is a function g or j. Okay, you can find it in, well, Wikipedia or in Mathematica, and they say j is equal j absolute invariant, whatever. So the fact that they're very complicated functions to work with. There are lots of fun working with them. Plotting potential is a hard work. Solving differential equations is much harder work. But what you see here is this. If you take this potential, which is some function of this function g, and these are 2 complex variables. Now I'm plotting everything like for complex variables. So you have here nice inflationary potential, but here you have some wild forest, which is totally, absolutely uncontrollable, at least the first time when you look at it. You do not understand where it is, where it happened. And so the answer is that these functions, they are often represented in mathematical literature as a series, like e to the I, whatever, q, and e to the I minus q, and an infinite amount of terms. And if you're lucky, in some limit, you can calculate the sums, and they are easily calculatable here, so where everything is smooth. When you plot this potential using Mathematica, using whatever program who knows this function better, then you see this stuff. And the further you go down, the stranger it goes. Now, of course, we do not care, because this is where inflation. And then after inflation, you roll down here, and then you oscillate here. You never go to the forest unless you just roll there. And that is interesting because I don't know what kind of animal may will find you in the forest, but it's just strange. It's interesting. You want to know what these fields are about. So you take a counterplot, and the counterplot show you fractal picture of this red minima. All of this red minima has the same depth, 0 or cosmological constant, because cosmological constant is also SL2Z invariant. So if you add it, that's fine, but all of them has the same value and have this fractal distribution. And this is fractal, I just cut the tops. That's how I get this. And then I cut the bottoms, and that's how you get this fractal distribution of mountains, which go all the way here, okay? Now, if you want to work with alpha attractors, you want to switch to a beta coordinates, because in these coordinates, you do not see these exponents yet here. So you change variables, and you switch to the variables like that. Then you will see this attractor behavior here and everything. And the potential in this direction, this is actually axion field. And by the way, pay attention to this, Kati, because this is natural inflation if it rolls in this direction, because this is axion, which was discussed first, okay? So that's a very interesting thing. But we are playing with this part as well, and we can roll down in this direction, get the inflation which I mentioned during alpha attractors. And we know that inflation easily happens here. But here, of course, this is just all this wild forest, so it's hopeless. Katya, you'll have it's already in the archive as of yesterday. So yeah, all the pictures are there. Now, the thing that it's very difficult to understand this. It's really like a hell, okay? But the reason is that in these coordinates which we use, you have this y squared, which is exponent standing here. And therefore, all images at large negative phi are exponentially distorted. And therefore, you need to have a coordinate system where this distortion is minimal. You cannot avoid distortion because the true geometry of this modular space is hyperbolic geometry. Sorry, cannot be helped, but it can be at least some relief reached if you use the coordinate system, which is called Killing coordinates. We used them a long time ago for alpha attractors, such that this metric is symmetric here and here, and it does not depend here. The bad thing that it was exponentially sensitive to value of the field phi. Here it does not depend on the field phi at all, and at reasonably a large extent of the field theta, everything is almost kind of canonical. And now when we do this, we switch to something. When I first seen it, and Renata suggested, Carlos suggested to do this, and I did not believe it, I started replacing it this way and that way. Where all of this forest? It was downstairs. Now all of this forest is here on both sides. And what is this? Oh, and what is this? Ah, this is image of what was previously the upper part, which was perfectly flat, going to infinity with all of this red minima along it, okay? And now it is not flat. It is like an island. It does not matter because you can study inflationary perturbations in the system of units which is more comfortable for you. So I can do whatever I want in this coordinate system, but this is for understanding of general structure of the potential. So this is now equivalent to that, okay? Now, this is equivalent to this. They are similar. They are in the coordinate system, which is invariant with respect to certain, well, this SL2C transformation, as well as this one. So now this is equivalent to this. But this was previously was this ridge. So now what I say is that in this coordinate, this ridge is equivalent to all the upper part. Well, that's already an interesting game. And it was very, very difficult to absorb this all information because it's pretty weird. Okay, so this is a part where you see several different ridges. And this is an image of this one. And this is an image of this one. And then I make several different steps. So first of all, this is what I said. We identify this part with this part because there is an invariance with respect to switch, simultaneous switch of phi to minus phi and for theta to minus theta, which is equivalent to just rotating it. Okay, so if you rotate it on 180 degrees, this is what happened. In fact, this one is just symmetrically invariant. But for more complicated situations, this symmetry, just like that, is not sufficient. You need to do this. And this is a part of this SL2Z. So we're not violating anything. And when you see that these two animals are equal to each other, this means that they are. If we see that this one looks equal to this one, because it works across like that, okay? Then these parts are equivalent to this, physically equivalent. Meaning if you start rolling from here, you can equally well start rolling from here. These pieces are equivalent. Now, I know that these pieces are equivalent too, because they are obtained by plotting this same thing in a different coordinate system. So all of this in infinite chain of axion minima, they are here like a necklace, okay? And this is another chain of minima, which is a necklace around this thing, okay? And now, next step, we say that this one is equal to this one, which I already mentioned, and therefore this one is equal to this one, which means that this ridge is equivalent to the whole infinite area here, okay? That was very, very difficult to understand, but then we continue further. And this is this upper part, just a little bit more extended. So we can apply this procedure to every single part of this. So this is a central ridge. This is from the point of view of those who study this geometry. This is fundamental domain. And then this is the central ridge. But all of these ridges, because it's like axion theory, everything is periodic. And they are just really equivalent to each other. This is also a part of this SL2Z transformation, this periodicity. So we've shown that this ridge is equivalent to everything here. But this ridge is equivalent to this. This is equivalent to this as well. Therefore, each of these infinite series of ridges is equivalent to the whole infinite plane where you can have inflation, which means that inflation can be here, and here, and here, and here of this ridge. Now notice that there's some family actually going all the way down, infinite number of them, family of baby ridges attached to the small ridges, but because this baby ridge attaches to this one, and this was equivalent to this. Anyway, what happens is that there's infinite number of these very, very sharp-looking ridges. Each of them is equivalent to the flat space where do inflation whatever you want, and there are infinitely many of them. So that's the main lesson so far. So we have that these models with this symmetry have inflationary potentials, and they describe infinitely many inflationary plateaus. And now in the end, we decided with help of some other our friends to make a transformation, to transform it to even a better view, which is using something which is called Haley transform, where you transform this half plane in which we complex plane where we made all this study to another one, which is disk variables. And that is a famous Escher paintings. So this one show you the half plane, and this show everything the same in disk variables. The same physics, the same story here. And this is the potential how I see it. So this looks magnificent, like from these movies of the person with a shield having, okay, this is what was our huge plateau, which was infinite plateau, which is the only part which occupy most of the picture. But this is the central ridge. These are some other ridges. There are infinitely many of them. Each of them is inflationary plateau. And this is still another set of coordinates which are closer to original ones. You see, this one which I've shown you before, it does not show how it all ends. It goes to infinity because, well, because it's this Escher disks, or it's called Poincaré disk. Poincaré disks seem finite, but in the proper coordinates, it expands to infinity. But if I want to see the whole thing with all of its glory in a finite picture, which I can show during the talk, and this will be my last talk before the movie. Okay, last slide before the movie. So what happened in these variables? This is everything. The infinite number of these peaks surrounding, oh, this is my original plateau. This is the infinite part which attached my attention. And this one, the central ridge, looking at which I've written in the first version of my paper, I've written, it is impossible to have inflation there. So I was wrong to replace the paper because this is equivalent to this one. And then all of the others, they're equally good. And how do you know that they're equally good? Well, you try to look at it, like go closer, like to a friend, try to travel in this direction. So how you travel to this direction? Change coordinate system and do it continuously. And then you make a movie. And does it work? What? What? It does not. Who promised me that? Okay. Can we switch to the real movie then? We checked it so many times. Windows. Just switch to the real movie. It will be even better. Oh yeah, it works. How will you do it? Magic. So, thank you. So what happened is that this peak is unmovable. This is our central part. This is the original father of everything, okay? This, when it comes here, at this moment, it becomes a central ridge. But essentially, each of them, they're coming from infinity. They're far, far away. They come here, and then at that moment, they stop here and kiss the the hand of the emperor. Now the equivalent, now another equivalent. There are infinitely many of them. So you see, I wanted sometimes to talk to Stephen and to show them this beauty which we're playing with, which is so amazing what we are doing. And in part, it is because of him. Thank you very much.
Any questions?
I want to check if I understood anything you said, Andrei. So does this mean that there are infinitely many values of the original parameters which end up with the same physics?
Yeah, I'm saying that you just plot your potential. You did it once. But when you plot this, you see some small stuff, okay?
Right.
And
but if you took another value of the parameters, you'd be at another.
No. I never changed any parameters. Nothing like that from a different point.
You're just changing coordinates.
Yes, okay. So it's just different things. But what is important that the change of coordinates is compatible with original symmetry. So I am not tricking your eye to seeing something which is not there.
So does that mean by changing coordinates, you see a different value of initial places to inflate from and stuff like that?
Yeah. It's not about initial places. It's just the whole potential. It's this hyperbolic. It's like in this Escher thing, there are infinite number of devils and angels. Okay, and close to the boundary, they become smaller and smaller and smaller.
But in fact, they're all equivalent.
But in fact, they're equivalent.
I wonder if they're merely equivalent or if they're describing actually exactly the same physical value in different coordinates. Basically, is our space the space of tau or tau modulo SL2Z?
Yeah. There is an interesting and very important question, which we all think that we have an answer to, but then I think that it is requires much more time that we have right now. They think that in string theory, you have something like fundamental domain where everything is described and everything else is just copies of it. Well, this is not string theory. This is string-inspired supergravity. And in string-inspired supergravity, you start with this fundamental domain, you start inflation, and then inflaton field goes down and crosses the boundary, because the fundamental domain in this approach is not geodesically complete. So it's just like with Schrödinger, the boundary or the horizon of the black hole. There is still black hole inside.
No, but there's a difference. The fundamental domain has orbifold singularities of order 2 and 6. If you unfold that, you get a space without, so just the metric, forget about the potential for a second.
Yeah.
The fundamental domain has orbifold singularities, and the upper half plane, or the hyperbolic disk, whichever you want it, has no such metric singularities. It's a homogeneous space. Every single point looks like every other point.
Yeah.
And you put this SL2Z invariant potential on it, and you can make beautiful movies. But every point, every copy of the fundamental domain is absolutely the same as every other copy. But again, you know, when you actually take the quotient, you have fixed points, so orbifold singularities.
Well,
I know. That's qualitatively different.
Yeah, I know. We discussed it with several different people, specified in string theory, etc. And my understanding of this, we are talking about slightly different things. Once we say, I study right now this, and this is supergravity, and this is superpotential, and this is metric of this, then I study physics without referring exactly how this model was appeared being motivated from consideration of string theory with orbifold. No notion of orbifold appears in the construction which we use.
We have a question online. How is this different than modular invariance and the conjectures of Vafa, et al. And Swampland?
Vafa?
VAFA.
I don't know.
I think I can add a little bit from string theory. So one way to disambiguate whether you're supposed to live on the fundamental domain or you're supposed to live on the unwrapped space is to add more generic ingredients. And we do know that axions couple to fluxes and branes in such a way that there are different branches of the potential, but the potential is unwound. This is the monodromy effect. And so that's a way of seeing that there's meaning to the larger field range of the axion than the original underlying period.
Yeah. Well, we can discuss it further. What I can say, for example, if I wanted to understand the structure of the central ridge, which is just what I see, okay, in this coordinate system with this potential, I'm talking about the certainty that this picture does exist here. I try to interpret it, and the first idea is that here's a fundamental domain, and I make a modular image of the fundamental domain because it actually looks similar to this ridge. And then when I make a copy the image of the fundamental domain, it covers only a tiny part of this ridge. So I guess this just, we do whatever we can do using the change of coordinates.
Yeah,
And
I'm just saying that in string theory, the global picture is symmetric. However, it involves changing flux quantum numbers, brane quantum numbers, and so on to see the full symmetry in general.
okay.
All right. Thanks again to our speaker.